Now, how about if there are four forces acting on an object, like the one in this illustration? So there is an F applied at an angle. There is another force, Fn or N, and there is another force, Mg or Fg, and the fourth one is F sub F. This one F sub N, this one F, and this one is F sub G or Fg. Okay, so let's say this object is being pulled at an angle theta. That is force 1. The first force is F. The second one here is called the normal force, or F sub N. So what is a normal force? The normal force here, as you can see, is upwards. The normal force is a contact force. So there's no normal force if there's no contact between two surfaces or between two objects. So normal force is a contact force that is exerted by a surface or any surface to any other object. So here, the normal force is from the surface of the floor, okay, from the ground. So surface of the floor is exerting a normal force to the surface of this object, this box here. So aside from the normal force, there is another force acting on this object, and that is the force of gravity or force of weight. So gravity is acting upon this object. So how do we get for the force of gravity? Remember from Newton's law, we discussed that the force of gravity is equal to the mass of the object times the gravitational force or acceleration due to gravity. The g here is equal to 9.8 or 10 meter per second squared. So let's write g here. Okay, recall that g, or gravitational acceleration, is equal to 9.8. So it's 9.8 meter per second squared. So meter per second squared. Okay, or 10. So let's use 10 for easier calculations later. Okay, so let's represent weight with the symbol Fw or Fg. So Fw for force of weight, Fg gravitational force or force of gravity. Okay, and then the last one is the force. This is in opposite direction of the displacement. Okay, so as the box moves to the right, there is a resistive force pulling it to the left, trying to slow it down, and that is called F sub F, Ff, or frictional force. So let's call this friction. We can write the symbol F here. You can also use the symbol Ff, which means frictional force. All right. So the four forces are the applied force here, the normal force Fn, the frictional force or friction, and the force of weight or force of gravity. Okay. So how are we going to get the total work done by the four forces acting on this object? Okay. So this one is actually case 4, right? N is perpendicular to the displacement, 90 degrees. So this is case 2, okay? How about the force of weight here? The weight of the object. Weight of the object is also perpendicular to the displacement. So that means the theta here between the F and the S is equal to 90 degrees. And the last one, the friction or frictional force or force of friction, is case 3, right? case 1, case 2, case 3, case 4, case 2, this one, case 2, this one, case 3. Okay, so let's say that we erase. Now let's recall. Okay, the big F is the applied force, could be a push or a pull, and its unit is in Newton. N, let's write that as Fn, F sub n, the normal force. And the weight, let's write it as force of weight or Fw. And for friction, let's use the symbol Ff, force of friction or frictional force. Okay, all of these are in Newton, in units of Newton. Okay, first one, case 4. So remember this, right? We discussed already how to solve the work done here. This is case 4. Now, how about the normal force? How do we get for the work done by the normal force, Fn? Theta is 90 degrees, case 2. So 0 work done by the normal force, N. How about for the third one? Yes, this one. Force of weight or force of gravity, mass times G. So perpendicular to the displacement or motion of the object. So there's no work done. This is still case 2, 0. How about for the force of friction or frictional force? Friction is in opposite direction of the motion of the object, opposite the displacement. So cosine of 180 is -1. So the work done is friction, force of friction, or friction times S. And then you have the negative from -1. So there is negative work done by the force of friction. So work done by friction or work done by frictional force is equal to negative F, negative friction times the displacement. How about the last one? Okay, how are we going to get the total work done by these 4 forces? Total work done by 4 forces is equal to, of course, the work done by the applied force, work done by the normal force, work done by the weight, and the work done by friction or force of friction. So since this one is 90 degrees, so this is 0, cosine 90 degrees is 0. This one, force of weight, is also perpendicular to the displacement. So cosine 90 degrees is also 0. So we are left only with work done by the applied force and work done by the negative work done by force of friction. Now combine that, you have F S cosine of theta minus the frictional force times displacement. So this is the total work done. This is the formula. This is the formula if you have like 4 forces acting on an object. Okay. Now graphing work. How are we going to graph work? Let's say case 1 here. You have the force is in the right. You're pulling the object to the right, and this displacement is also to the right. So if you're going to graph this, you will get this kind of graph, a rectangular graph. So the area under the graph is equal to the work done. So the area of this is equal to work done on an object. So F times S is equal to work done. So this is like when you get the area of a rectangle, you just multiply the length by the width. So length times width. So that's S times F or F times S. Okay. Always remember that work is equal to the area under the graph. And since that is a rectangle, the area of a rectangle is always length times width. That is why it's S times F or Fs. How about if the problem is like this? So if the problem is like this, you will get this kind of graph, a trapezoid. So if the area under the graph forms a trapezoid. And this area under the graph is, of course, equal to the area. Remember that to get the area of this trapezoid, you need the formula 1/2 base 1 plus base 2 times height. So here you have base 1, and here you have base 2. Okay? So you add base 1 plus base 2 times height divided by 2. Okay? Or you can also do this by getting the area of the square here plus the area of the triangle here. Okay? But the easiest way is to get the area of the trapezoid. So as long as you know the area of the trapezoid, you will get the work done on the object. So how about this one? How about if the force is applied on the spring like this one? Okay, like in this illustration. So if you stretch this spring, apply a force and stretch the spring, this will stretch. There will be an elongation here. Okay, there will be an increase in the length of the spring if you stretch it with a force F. So the elongation is equal to X. That is equal to S, or the displacement. So X is the elongation. So the added length or the elongation after you stretch the spring or after you compress the spring. So the spring can be stretched, it can also be compressed. So gives you, when you graph it, it gives you a graph that looks like this one. Remember that the force, the bigger the force you apply, the longer the elongation of the spring. So F and X are directly proportional to each other. So it gives you a straight line graph like this one. And the area under the graph is equal to the work done on the spring, work done by the force on the spring. So the area in the graph forms a triangle. And to get the area of the triangle, you need area equals 1/2 base times height. So work is just equal to the area of the triangle, which is 1/2 base times height. So what is what is the work done on the spring? Work done by force on the spring. That is 1/2 times the base times the height. So the work done on this by the force on the spring is 1/2 F times X. Okay? 1/2 F times X. And don't forget Hooke's law. Remember, we discussed in the previous lesson, we discussed F is equal to Kx. Okay? Let's recall that because it's important. Hooke's law. According to Robert Hooke, the proponent of Hooke's law, he said that the force is equal to Kx. What is K and what is X? So we call this Hooke's law. That's right. Hooke, Robert Hooke. K, Hooke. And then, so Hooke's law. So let's recall Hooke's law. What is K here? K here, X here is the elongation and F is the applied force. According to Hooke's law, the force is directly proportional to the X. The bigger the force you apply, the longer the elongation or the stretching or the compression of the spring. Okay? And the K is called the spring constant. So spring constant is the measure of the stiffness or elasticity of the spring. So springs are made of different materials. Different springs are made of different materials. And these materials have different elasticity or stiffness. Okay, the more stiff the object is or the material is, the more difficult it is to stretch the spring. or the material. So it is a measure of the elasticity of an object. That's K, spring constant. So let's say elasticity. For example, rubber. When you stretch rubber, it has, and when you release the force, okay, it has the ability to return to its original shape or original position. So that's elasticity. So springs, rubbers are elastic. Elasticity means the object returns to its original shape or position. Okay, after applying force. So you stretch the spring and then you release it. After you release it, the spring returns to its original shape or position. That is called elasticity. So that's K. The force is equal to Kx. Hooke's law. Okay, and let's continue to the next. Okay, let's erase this one. Clear. Let's erase. The next. Okay, example. So in an example here you have a graph of work done on an object. Okay, a 40 Newton force was applied on an object, and it moved a distance of 10 meters. The displacement is 10 meters. When you applied 20 Newton force on an object, it moved 5 meters. When you applied a force of 40 Newton, the object moved a displacement of or a distance of 10 meters. So here, if you want to get the total work done, you just add the work done by A and the work done by B. Okay, force A, force B. Okay, work done by force A plus work done by force B. Work A, the area under the graph forms a triangle. So we can have 1/2 base times height. So what is the base? What is the height? So this one is 1/2. So let's write 1/2. The base is 5. So 1/2 base times the height. What's the height? 40. 40. So height is 40. So 40 times 5 is 200, right? 5 times 4 is 20. 0. So 200. 1/2 of 200 is 100. So let's type 100. 100 joules. How about work done by force B? Also this forms a triangle. Smaller triangle. So let's have 1/2 base times height. So what's the base? The base is here. So 10 meters, 5 meters. So that's also 5 meters. 10 minus 5 is 5. Then multiply that by the force applied. So force applied is, the height is here. 20 meters, right? 20. So 5 times 20, 20, 20 newtons. So 20 times 5 is 100. 1/2 is, of course, 50. So 50 joules. So the total work done is 150. So you just add. So 150 joules. Okay. Next example. Let's erase that and go. Let's move on to the next example. Okay. In this example, you have force of 6 newtons and a displacement of 4 meters. So what's the total work done here? Here you have a trapezoid. The area under the graph is a trapezoid. So you just get 1/2 base 1 plus base 2 times height. So 1/2 base 1 is 2 here, and base 2 is 4. So 2 plus 4 times 1/2 times 6 newtons. The answer is 18 joules. How about in the next example? Now in this example, you have a graph above the x-axis and another graph below the x-axis. How do you get for the total work done? So always remember, the graph above the x-axis, the area above the x-axis is positive. The area or the work done is positive. And the x-axis is means there's negative work done here, minus. This one is positive work, this one is negative work, okay? Above, below the x-axis, always remember that. Okay, so how we're going to get the total work done here? If you have this graph, we are given this graph. So area of work done by force A, work done by force A is equal to 1/2 base 1 plus base 2 times the height. That gives you 36 joules. And the work done by force B is 1/2 base times height. Because this one is a triangle, you use 1/2 base times height. This one is a trapezoid, so you use 1/2 base 1 plus base 2 times height. So here, work done is 2. Okay, so above the x-axis positive, below the x-axis negative. So therefore, what is the total work done here? So that's WA minus WB. So 36 minus 2 is equal to 34. So the total work done is equal to 34 joules. Okay, how about power? The rate of doing work, how fast you do the work, is called power. So which machines, let's say you have machine A and machine B, and machine A has a power of 100 watts and machine B has a power of 200 watts. So which one has a higher power, higher rate of doing work? Okay, so of course the 200-watt machine, right? So rate means time, the time it takes to do the work. Okay, work done per unit of time. So that's the work done per second. So that is called power. Work done per second. Now, so power is work done per second. So in mathematical form, in equation form, power is equal to work over time. So work is in joule and time is in seconds. So the unit is joule per second or watt. So 1 watt is equal to 1 joule per second. Symbol for watt is W. So 1 joule per second, 1 watt, 10 joules per second is equal to 10 watts. Okay. So the main formula is work over time. And we can derive different equations of power from the main formula. So since work is Fs, then we can also write power as F times S, or force times displacement over time. But remember that S, displacement over time, is equal to velocity. Since displacement over time is equal to velocity, then we can write power as force times velocity. So let's write that. So this one is, okay, wait. So let's see. Okay, this one, S over T is V. So you can write this as velocity. So this is force, right? Force times velocity. So we can write power as force times velocity. So this is derived from the main formula, work over time. Okay. Let's erase that. Let's continue. Okay. So how about if these are the sample illustrations. So for this kind of letter A, if you're given this kind of problem, then you just get the power, you just divide the work over time. Letter B, this illustration B, if you're given the force, the time, and the displacement, how do you get for the power? So you can use the formula Fs over time. And of course, letter C, illustration C, if you're given the force and the velocity, you just multiply Fv and you get the power. Okay. How about this one? Illustration B. Let's say you have a box. You drop the box on the floor. Okay. So how much power is being expended as you drop the box to the floor? How much power? So remember that power is work over time. Can also be written as F times S over time. And since the force of weight or force of gravity is equal to mass times G, we can change this F into Fg or F weight, and that is equal to mg. So F, instead of F, we write mg and then multiply by S divided by T. So for this kind of situation, you use power is equal to mgs over time. Okay, S is the height. The displacement in the y direction, Sy, equal to the height. Okay, how about the next one? How about here? How about if we have this illustration? Here you have a spring. The amount, okay, the string is stretched. String is being stretched with a force of 10 newtons. And the elongation is x or s, which is equal to 0.4 meters at a time 2 seconds. So how much work was done by the force on the spring and how much powers was expended? Okay, so work is equal to, remember, work is equal to 1/2 F times X. We already discussed that in our um, we discussed that a while ago. Work is 1/2 F times X, or could also be 1/2 kx squared. Remember that Hooke's law states that F is equal to kx. So the x here, the F here, okay, let's annotate that. Remember Hooke's law, the F is equal to kx. According to Hooke's law, F is equal to kx, spring constant times x. So you can substitute kx into the equation and you get kx times x. So you have here k times x times x. This is another x. So you have 1/2 kx squared. So you can write work using the formula. You can get the work done by using the formula 1/2 FL times x or 1/2 kx squared. And of course, to get the power, you just use the formula work over time. And work is equal to Fx. 1/2 Fx over time. Okay? Work is 1/2 F times x. Okay. So that's Fx over time. The 1/2 is here. Over 2 times time, 2t. And or you can write it as power is equal to k, spring constant, times x squared over 2 times t. Okay? Okay, a constant horizontal force is force of 10 Newton, a constant horizontal force of 10 newtons, is required to drag an object across a rough surface at a constant speed of 5 meters per second. How much power is being expended, and how much work would be done in 10 minutes? Remember, 1 minute is 60 seconds. So 1 minute is equal to 10 minutes is equal to 600 seconds. Okay, let's solve this. So how much power is being expended here? So remember that power, you have the velocity given and the force given. So we can just use the formula F times V, force times velocity. So remember that power is equal to F. Okay, force times the velocity. So 5 times 10 is 50. So the answer here is 50 watts. So let's have 50 watts. Here you have 50. How much work would be done in 10 minutes? So work is how much? What formula are we going to use here? The time is 600. 600 seconds. 10 minutes. Remember that power is work over time. Power is equal to work over time. So if you want to get the work, you need to multiply power by time. Okay, multiply power by time. So work is equal to power by time times time. Power is 50, right? This is 50. And time is 600. 600 seconds. So the answer is 30,000. The answer is 30,000. So 30,000. 0, 0, 3 zeros here. So 30,000. And the unit is joules. 30,000 joules. All right. Next problem. So let's say we have a cart was pulled along a handle with a force of 100 Newton for 10 minutes. If the handle made an angle theta of 30 degrees with the direction of motion and the cart moved through a distance 6 meters, A, how much work was done, and B, how much power was expended in 10 minutes. Okay, so let's solve for the work done. So the work done, the force applied at an angle 30 degrees. So let's use, this is case 4, right? No. Yes, this is case 4. So work is Fs cosine of theta. Okay, Fs work is equal to Fs cosine of theta. Case 4. So F is 100 F times the S, which is 6 meters. So 6 So Fs and then cosine of theta. What is cosine? Okay, cosine of, let's write cosine of 30. So what is cosine of 30 degrees? So remember cosine of 30 degrees. So cosine of 30 degrees is equal to square root of 3 over 2, or 0.154 square root of 3 over 2. Okay, let's turn to this one. So let's have square root of 3 over 2. So the answer is 600 square root of 3 over 2. Then we have the square root of 3 over 2. So what is 600 and square root of 3 over 2? Square root of 3 over 2, the answer is 519.6. 519.6. So 0.6 joules. Okay. Now how about the power being expended in 10 minutes? Remember that power is work over time. So power is equal to work over time. Time is 10 minutes, which is equal to 600, right? 600 seconds. And then the work done is 519. $519.6. So the answer is 0.866 watts. 0.866. 0.866 watts, or 0.9 watts. Okay. How about this example? How much work was done on this object? And how much power was expended after 4 seconds? So time is 4 seconds. What is the power expended after 4 seconds? So how do you solve for this? Work A. So work done by force A and work done by force B. So above the x-axis, positive. Below the x-axis, we have negatives. This one is a trapezoid. This one is a triangle. So let's have 1/2 base 1 times base 2. So here you have, okay, let's write 1/2. Since it is a trapezoid, we have 1/2. Let's multiply that. 1/2 times base 1 is 1 meter and base 2 is 3 meters. Okay, 1/2 base 1. So 1 meter plus 3 meters. 1 plus 3. 1 plus 3. Then times height. Height is 14 newtons. Okay, 14 newtons times 40. So how much is that? Okay, 4 times 40 is 160. 1/2 of 160 is 80. So 80 joules of work. Here you have 80. How about here? Triangle. So it's 1/2 base times height. So 1/2. The base is 2. 2. So let's have 2. 1/2 base times height. Base is 2 and the height is here. The height here is 20. So this is 40. So of course, half of 40 is, so you cancel this 2. So you are left with 20. So the answer here is 20. So if you add, to get the total work done, you have positive 80 and negative 20. So this is WA minus WB. So 80 minus 20. And 80 minus 20 is 60. So 80 minus 20 is 60. So how much power was expended after 4 seconds? So power is the total work done after 4 seconds. So after 4 seconds, the power expended is work, total work, sigma work, or the total work divided by 4 seconds. So here you have 4 seconds. So over time. So this will be 60 joules, 80 minus 20. So 80 minus 20 is 60 joules. And time is 4 seconds. So 60 over 40 is equal to, no, not 40, but 4. 60 divided by 4 is 15. So the power is 15 watts. So the answer here is 15. All right. How about the next one? How about here? How much power, no, how much work was done by the force on the spring? And also let's solve for the power expended after 2 seconds. So it took 2 seconds to stretch the spring here, and it elongates at a distance or elongation of 0.4 meters, 0.4. Okay, let's solve this. So this one is 0.4. 0.4. Okay, how much work? So remember, it's 1/2 F times X. So here, 1/2 F times X. So let's write that. 1/2 F is 100 and X is 0.4. So times 0.4. Okay, 0.4. So 100 times 0.4 is equal to 40. And 1/2 of 40 is 20. 1/2 of 40 is 20. So the answer is 20 joules. How about the power expended after or 2 seconds? Here it's 2 seconds. So that is equal to work over time, right? And this is equal to 20 joules over 2. 20 joules over 2. So 20 over 2 seconds is 10. So the power is 10 watts. Okay, all right. Okay, last problem. Let's say here you're given in this situation, there's a truck moving to the right. Its mass is 1,000 kilograms. Its initial velocity is 10 meters. Its final velocity is 20 meters. The time is 5 seconds. The question is how much power was expended after 5 seconds? Okay, its initial position is at point A and then final position at point B. So what's the power of the truck? The power expended by the truck after 5 seconds. Okay, so in this example, we're going to solve for the power. And this involves equations of motion. Okay, remember that power is work over time. And you can write work as force times distance divided by time, or force times displacement divided by time. And S divided by time is V. You can write power also as force times velocity. Now, recall that average velocity or velocity is initial velocity plus initial velocity divided by 2. So we discussed this in the previous lesson, equations of motion. So we got this, we studied this in equations of motion for uniformly accelerated motion. Okay, objects in uniformly accelerated motion. So equations of motion, remember that acceleration is equal to initial velocity minus initial velocity. Final velocity minus initial velocity divided by time. So we got this equation also from the equation of motion V is equal to U plus AT. Then formula transformation, you get acceleration V minus U over T. Remember that acceleration is change in velocity over time. So final minus initial velocity divided by time is acceleration. Now, we're gonna need that later in order to solve for power. Remember that power is equal to force times V, velocity or average velocity. This F here, we can change this into MA, Newton's second law, mass times acceleration. So substitute mass times acceleration to this quantity F, and then multiply MA by average velocity of the truck, okay? Average velocity of the truck times the acceleration of the truck times the mass of the truck, okay? Now, remember that average velocity is V plus U over divided by 2. That's the average. You get the initial and the final. You add the initial and the final velocity. And divide it by 2 and you get the average velocity. So you substitute that in this quantity, which is velocity. How about for acceleration? So acceleration is V minus U over T, final minus initial velocity divided by time. Okay, change in velocity per unit time. So that's V minus U over T. Now mass times V minus U over T multiplied by quantity V plus U divided by T. Now, if we are going to, if you notice, V minus U multiplied by V plus U will give you V squared minus U squared. So mass times V squared minus U squared over 2 times time. So our new formula is P is equal to mass times V squared minus U squared. U squared. And then divided by 2 all over 2t. So 2 times time. Okay, substitute. You plug in all the values into this equation and you get power is equal to, so let's solve that. Power is equal to, so let's check again. Let's check the values. So let's plug in all the values. Mass is 1000, U is 10, V is 20, and time is 5 seconds. So let's plug in all the numbers into the equation. Plug in all the values into the equation. And then let's solve. Okay, so what's the power after 5 seconds? So let's solve. Wait. Okay, let's solve that. So V squared minus U squared. So 20 is 400 minus 10 squared, that's 100. Okay, let's solve. Okay, wait. All right. So let's say you have mass is 1000. So let's have 1000 here. 1000 and then multiplied by V squared. 20 squared is 400, right? 20 squared is 400. Minus U squared, that's 10 squared. 10 squared is 100, so minus 100 divided by 2 times 5. Time is 5 seconds. So 2, try 2 times 5, and that's 2 times 5 is 10. All right. So how much power was expended after 5 seconds? Yes, time is 5 seconds. So final answer, that's 1000 times 300 over 10. So 1000 times 300 is how much? 300,000. Divided by 10, you have 30,000 watts. Okay, you're left with power equal to 30,000 watts. That is the answer. After 5 seconds, 30,000 watts is expended by the truck.